Good afternoon, all, and welcome to this very important lectures. So I welcome Professor Deepankar Banerjee for welcoming our distinguished guest. Professor Deepankar Banerjee, please.
It's a pleasure for me to welcome Ashoke and the rest of the people here in this very important seminar. Ashoke has been, really inspirational for many in our country. You will probably hear more about his credentials, why he is so famous. I'm also from Calcutta. He has also studied from Calcutta, then moved on. So when we were students, we heard about his credentials, and we were inspired to come into research. And these are the fields also. In our time, it was in infancy. It just started. So we were always little worried about this emergence of because we were in condensed matter. Those days it used to be called solid state physics. Now it is not called anymore solid state physics. So it's really a privilege for us to host Ashoke for a short while, and we are looking forward to this seminar and a journey to the universe with the physics as a basis. And thank you for coming. Yeah.
Thank you, sir, for welcoming our guest. So it's now my formal duty to introduce our speaker. So it is indeed a great pleasure and honor for me to introduce Professor Ashoke Sen, the ICTS-Infosys in Madhava Chair Professor at ICTS-TIFR at Bangalore. Professor Sen earned his MSc from IIT Kanpur and PhD from High Energy Physics from Stony Brook University in New York. After completing postdoctoral research at Fermilab and the Stanford Linear Accelerator Center, he joined TIFR Mumbai as a faculty member. He later moved to the Harish Chandra Research Institute at Allahabad, where he spent over 20 years. Additionally, Professor Sen holds positions at Morningstar Visiting Professor at MIT and Distinguished Professor at the Korea Institute of Advanced Study. Professor Sen has been making groundbreaking contribution to the foundational physics, particularly in the development of string theory, a framework that aims to unify the fundamental forces of nature. His pioneer work in demonstrating that all string theories are distinct limits of a single underlying theory has been hailed as brilliant by other prominent figures in the field, such as Fields medalist Edwin Witten. His achievements is considered a major breakthrough in our understanding of string theory. Professor Sen was among the inaugural recipients of Breakthrough Prize in Fundamental Physics for his revolutionary work on string theory. A fellow of the Royal Society FRS in London, he was received numerous prestigious honors, including the ICTP Prize, the Dirac Medal, the Third World Academy of Sciences Prize, the Pius IX Gold Medal, the Sant Swarup Bhatnagar Prize, the Infosys Prize, and the Padma Bhushan, among many others. It's indeed my privilege to invite you for this talk. Professor Sen, over to you, please.
Okay, thank you very much for this kind introduction and also for inviting me here. It's really a great honor for me to be here giving this talk at IIST. So today I'll try to describe briefly what, with our current knowledge, we can possibly say about the future of our universe. Okay. But before we talk about the future, I'll try to review some details of what we know about the present universe. Okay, in particular, the present expanding universe that we are familiar with. So the fact that the universe is expanding has been known for about 100 years. Okay. And the way we know it is that far away objects we find are moving away from us, and further away they are, more is their speed. Okay. And this phenomenon is summarized in a theory which is called the Big Bang theory. Okay. And by now, in fact, there are plenty of experiments that confirm this theory, that indeed the further objects are moving away at faster speed. Now, by the middle of 1990s, we had a good understanding of the theory. And the present universe was thought to contain mainly two kinds of sources of energy or mass density. Okay. The first kind was ordinary matter like stars, interstellar dust, etc. Okay. And the second kind was given the name dark matter. Okay. It's an unknown source that behaves as ordinary matter as far as the gravitational properties are concerned, okay, except that you don't see them. Okay, so we still don't know what dark matter is, but it is clear that there is indeed something called like a dark matter, because otherwise the expansion of the universe cannot be explained just based on the ordinary matter. And since gravity is attractive, it was believed that the pool of matter was slowing down the rate of expansion of the universe. Okay, you can imagine that if you have an explosion in space, okay, the objects will start flying apart from each other. But because there is gravitational force that acts on those objects, okay, eventually they'll slow down, okay, even though they may keep flying apart. But this changed in 1998, where there are two independent experiments, both of which involve supernova, okay, which are basically some faraway objects in the sky. Okay. So people examined supernova and examined how fast they are moving away from us. Okay. And based on those observations, what they concluded was that the expansion of the universe is accelerating instead of slowing down. In other words, the rate of expansion of the universe today is larger than what it was in the past. And this changed our whole understanding of the current state of the universe, because with ordinary matter and dark matter, it's impossible to explain why the expansion will accelerate. Okay, just as we said, if there are objects that are flying apart because of some initial explosion, they may continue to fly apart, but gravitational pull is supposed to slow down the rate at which they are flying apart from each other. So the best explanation that we have today of this expansion is that 73% of the energy density in our universe exists in an unusual form, which is called the dark energy, or what is also called the cosmological constant, which was first discovered by Einstein, in fact. And the way it explains the accelerated expansion is that this dark energy has negative pressure, and this is what causes gravity to act as a repulsive force. Okay. And again, this follows from Einstein's theory of gravity. As soon as you include the effect of dark energy as one of the things that are driving the expansion of the universe, you automatically have this accelerated expansion. Okay. So 73% of the energy density is dark energy, and the remaining 27% is made mostly of ordinary matter and dark matter. Okay. So this discovery of dark energy, even though it looks like a technical discovery, okay, this in fact has drastically changed our perspective on the future of our universe. Okay, indeed the far future of our universe. Okay. And today's talk will be essentially the story of the future of the universe. Okay. And it may also be the story of our future, provided we survive various exciting events that may occur on the way, like pandemics, nuclear war, climate change, and asteroid impact. So I'll begin by describing what I call the classical story. Okay. This is a story that of how our universe will evolve with time if we ignore the effect of quantum mechanics. And then in the second part of this talk, I'll describe the effect of quantum mechanics. Now, we have already said that the presence of dark energy causes the universe to undergo an accelerated expansion. This is a consequence of Einstein's theory of gravity. Furthermore, what one finds is the dark energy density remains constant as the universe expands. Okay, this is the second surprising feature of dark energy, which is related to the first surprising feature, that is, it has negative pressure. Okay, and this is very unlike ordinary matter, because ordinary matter will get diluted. As the universe is expanding, the density of matter will fall, because the same amount of matter is now spread out in a larger volume. Okay, this doesn't happen for dark energy. The dark energy density remains constant as the universe expands. Okay. And this means that the acceleration that you see today will continue in the future. Okay. And in the far future, the effect of ordinary matter will basically go away, because they will be diluted away, okay, to very, very small values. Okay, so the universe will be dominated by dark energy, and at that time the size of the universe will double in about every 12 billion years. So due to this accelerated expansion of the universe, it is in fact physically impossible for us to reach very far away places in the universe. In fact, what one can show is that even if we travel at the speed of light, we can reach objects which are at most at a distance of about 18 billion light years from us today. Because even a light signal sent by us cannot reach points which are today 18 billion light years away. And it's essentially because of this accelerated expansion of the universe, those points are also moving away from us, right? So as the light signal travels towards those points are also moving away from us. Okay? And 18 billion light years is the limit of how far we can reach. So technically, we say that these objects are outside our horizon. So the horizon essentially is a hypothetical surface which tells us to what extent we can send signals. Furthermore, as the universe expands, more and more objects will go out of our horizon. And this is as if the universe is becoming a multiverse, which means it has multiple universes that cannot communicate. It's not that the universe, there is a sharp boundary between these different universes, but the universe basically splits up into different domains, okay, which have the property that you cannot send signal from one domain to next domain. So it's as if those domains don't exist, because even if they get destroyed for some reason, there is no way we will know. And this limited concept of what we mean by multiverse, in fact, is not a hypothesis. Okay, it in fact exists today, because today if we look out in the sky, okay, the farthest we can see in the current universe is about 45 billion light years. Okay. So you see that the 45 billion light years is already larger than the 18 billion light years, which is the limit to which we can reach. Okay. So this means that even our currently observed universe, okay, already has various regions, okay, which cannot communicate with each other in the future. Okay, if anything happens to those regions today, there is no way we're ever going to know that something has happened there. Now, at this same time, I should add that even though the expansion of the universe pulls different regions apart, it will not pull apart our galaxy. Okay, because galaxy, okay, the local density of matter in the galaxy is much larger than the dark energy density. Okay. So the effect of dark energy density cannot overcome the fact that there is local gravitational attraction between the objects in the galaxy. Okay. Dark energy is powerful simply because it's spread everywhere in the universe. Okay. Whereas the galaxies are localized objects in space. Okay. So the galaxies will remain intact. Okay, it will not be torn apart. In fact, our nearest large galaxy is Andromeda, and this is expected to merge with the Milky Way in about 10 billion years. Okay, so even the Andromeda will not be torn apart from us. But most other galaxies outside our local group will eventually go out of our horizon, which means that eventually we will be unable to communicate with those regions. Okay. So if we managed to establish civilization there today, okay, in those other galaxies, then eventually we lose touch with them forever. Okay, that it's theoretically it will become impossible to communicate with those faraway regions where we might establish civilization today. So in the far future, our local group of galaxies will be the only ones that will be within our horizon, okay, because of the local gravitational force between these galaxies. And when the last planet in that group cools down and becomes unlivable, life in the current form will not be possible. Okay, because as far as you know, life in the current form needs energy, okay, an energy gradient, and once the planet cools down to the extent that life is impossible, okay, then that will be the end of our civilization. Now we'll see that in the quantum world, okay, life will be a bit more scary, but certainly more exciting and adventurous. Okay. So this will be the end of the classical story, and now I'll say how quantum mechanics can possibly modify this story in the future. So the quantum story begins with that of a particle sliding on a hilly landscape. Okay, imagine that we have a landscape with two valleys, and you have some quantum particle that is free to slide in this hill. Now you know that there are two positions where the particle can be at rest. Okay, it can either be at this minimum A or it can be in this minimum B. Anywhere else, the particle will slide down. Now let's suppose that a particle is sitting at the point A, and then everyday classical experience tells us that it will continue to rest at A forever unless we disturb it. Okay, unless we give it a push, maybe it can climb up and go down to B. But according to quantum mechanics, there is a tiny probability that it may suddenly disappear from A, appear on the other side of this hill, and then from there it slides down to B. So this effect is known as quantum tunneling. But of course, you don't dig a tunnel, right? After the particle has gone from A to this side, okay, there is no tunnel that you see left over in the hill, okay, but the particle may simply disappear from A and appear on the other side and roll down to B. Now, we are not interested in particle, right? Our interest is in the whole universe. Okay. And the dynamics of the universe is described by what is called quantum field theory. Okay. Now, quantum field theory is a technical word, okay, but I'll try to give a simplified version of what quantum field theory is. Okay. So, field, we can imagine, is like having a particle at every point in space, okay, that moves in some hidden directions. Okay. So many of you are probably familiar with electric field, right? An electric field has three components, Ex, Ey, and Ez. Okay. And to specify an electric field, you have to specify the value of Ex, Ey, and Ez at every point in space, okay, and time, of course, because it cannot time dependence. Okay. So this you can think of as if there is a particle sitting at every point whose coordinates in some hidden dimension are Ex, Ey, and Ez. Okay, that's the sense in which we can think of a field as a particle sitting at every point in space and which is allowed to move in some hidden direction, okay, with the coordinates being Ex, Ey, and Ez. Okay. So at a neighboring point, for example, the electric field will be different, and that means that a particle at the neighboring point is at a different point in the hidden dimensions, in the hidden directions. Now we'll consider the simplest kind of field that we know of, okay, which is simpler than the electric field, and this is known as a scalar field. Okay. So the scalar field corresponds to having like a collection of particles at every point in space, but the particle moves in only one hidden direction. Okay. So instead of three variables, Ex, Ey, and Ez, we need really one variable, right, which is a function of space and time, right, which tells us that at the point X and at time t, what is the position of a particle in the hidden direction. Okay, that's the way you can think of a field. And just like the motion of a particle on a hill is controlled by the shape of the valley, right, shape of the hill. Similarly, the motion of a field is controlled by, again, something which is called the potential, and the potential V essentially plays the role of the height of the hill, okay, in the case of ordinary particle. So let's consider a form of V with two minima, just like we had the hill, okay, with two valleys. So V physically represents potential energy per unit volume. Okay, so if the field is here, then the energy density is higher. If the field is here, the energy density is lower. And if the field is here, then the potential energy density is even lower. So if you have a scalar field with such a V, such a potential, okay, then just like the particle, the scalar field can also rest at these two minima. It can either rest at A or it can rest at B. Okay. So we say that this theory has two phases. Okay. One phase in which the field at every point in space, okay, is sitting at the minimum A, or another phase where the field at every point in space is sitting at the minimum B. Okay, so these are the two phases of the theory. Okay. And here the word phases is used in the same sense as phases of matter. Okay. We know, for example, that if you have H2O, okay, molecules, then H2O can have water phase, ice phase, and steam phase. Okay. These are all different states. The theory is the same, right? It's the theory that describes how the H2O molecules interact with each other. Okay. But the realization of what state of the system it describes can vary, right? And the properties of the system can be as varied as between water, ice, and steam. Okay. So it's in that sense that A and B describe two different phases of the theory. So as I've already said, the properties of these two phases can be typically very different. Okay. And in fact, even the properties of elementary particles, like the mass and charge of the electron, can be different in different phases. Okay, here the mass of the electron may be heavier, here the mass of the electron may be lower. Okay, the charges can be different and so on. Okay. And in terms of this potential picture, we also have a very neat interpretation of what dark energy represents. Okay. The dark energy density, in fact, is the value of the potential at the local minimum. Okay. So today, for example, we know the dark energy that you observe in the universe is positive. Okay. And that basically means that if our universe had been described by the simple scalar field theory system, okay, then the phase that we are living in must be here and not here, because this has positive potential energy density. So here the dark energy is positive, whereas here the dark energy is negative. Okay. Now, unfortunately, our universe is not so simple, right? It's not described by a single scalar field. Okay. But I'll come back to this point later. Okay. But at this stage, it is just enough to note that dark energy density is essentially the height of this minimum. Now we consider the effect of quantum mechanics. Okay. So for this, let's again recall the case of particle on a hill. So if it was describing the rolling of a particle on a hill, then we have seen that the particle can sit either at A or at B at rest. And if the particle sits at A, then the classical laws tell us that it will keep sitting at A forever. Okay. But quantum mechanics tells us that there is a small probability that the particle will disappear from here, appear at the other end, and then roll down to B. So one can ask, can a similar tunneling happen in quantum field theory? So let me remind you again that in quantum field theory, the two phases that we have, okay, are that in one phase, the field at every point in space is sitting at the value A, okay, and in the other phase, the field at every point in space is taking value corresponding to this point, the other minimum. So you are asking, is if we are living in phase A, is it possible that it will suddenly make transition into phase B? Now it turns out that it does not happen everywhere simultaneously, right? That probability for that happening is essentially zero. Okay, because if for that to happen, the field everywhere in space has to tunnel from A to B. Okay, and that is very, very unlikely. In fact, the probability you can calculate and it's 0. But what can happen is that the field in some small region may tunnel from A to B. Okay. So imagine that this is the universe, right? And we are in phase A everywhere in the universe. Okay. What quantum mechanics allows us to do is to take a small region in this space and convert A to B in that small region. Okay. And larger the size of B, the smaller is the probability that it happens according to quantum mechanics. So once this happens, okay, then the classical motion takes over. Okay, and for this, let me again go back to the particle picture. Okay. Here, what we said is that the quantum tunneling, what it allows you to do is that this particle may suddenly appear on this side. Okay. But after it has appeared on this side, then going from here to the bottom is a classical effect. It will just keep rolling up and down, and if there is friction, then it will eventually settle down to B. Okay. The same is true here, that once quantum mechanics has produced this bubble, okay, after that it's the classical laws which tell us how the bubble will evolve. Now, you are probably familiar with the fact that any system tries to minimize its potential energy, right? If I drop an object, it falls because that way the potential energy will be lowered, okay? And the potential energy gets converted to kinetic energy. And this is true also for quantum theory, okay? That also for field theory, right? Classical evolution always tries to lower the potential energy. So once a bubble has been formed, right, it will try to lower its potential energy. And here it turns out that there are two competing effects. One effect is that it will try to, if it can lower its potential energy if it expands, because B has lower potential energy than A. On the other hand, this interface between B and A has a surface tension. Okay, so it costs energy to produce this interface, and as the bubble expands, the surface area goes up, so the surface tension goes up. Okay. So the effect of surface tension will be to try to pull this back. Now, a simple calculation tells us that once the bubble size becomes sufficiently large, okay, then it becomes favorable for the bubble to expand than contract. Okay, then to lower potential energy, the bubble will expand rather than contract, because the gain in potential energy from the interior of the bubble, okay, will overcome the reduction in potential energy from the interior of the bubble will overcome the gain in potential energy from the surface. So once quantum effects produce a bubble of sufficiently large size, then the bubble will begin to expand, and in that process it will lower its potential energy. And of course, the total energy is conserved, so the potential energy will go into the kinetic energy of the surface, and the surface will start accelerating. And as it accelerates, okay, it will accelerate continuously, and soon the speed of expansion of the surface will approach the speed of light. And eventually, it will convert A to B everywhere within the horizon. Okay, the bubble wall will expand at the speed of light, and everywhere where there is phase A, okay, it will become phase B. Nevertheless, okay, it will not cross the horizon. Right? We had said that there is a limit of how far we can send out light signal, right? And the bubble walls are also propagating at the speed of light, so they also have a limit that they can at most go up to the horizon but not beyond. Now one can ask, what will be the fate of any object in A during this process? And in fact, that is easy to answer. There will be total instantaneous destruction of any object that lives in A, because as we have discussed, even the elementary constituents like the electrons which would make up objects in A may not exist in B, or even if they exist in B, they have completely different masses and charges. Right? So the fact that the electrons and protons bind to form hydrogen atom, right, may no longer be true there. And even if it forms to bind something, right, its properties will be very different from the hydrogen atom that we are that makes us. Okay, and so the usual form of matter will be completely destroyed. So for this reason, it's apt to call this a killer bubble from the point of view of A. Okay. And A is also known as the false vacuum, because if the universe is in phase A, okay, then it gives the impression of being in a vacuum where nothing ever happens, except that once in a while a killer bubble destroys it. Right? Once a killer bubble is formed at any point in the universe, it expands and it destroys everything within the horizon. So now we come to the question that is of concern to us, okay, and that is, are we living in a false vacuum? So the possibility that we have been living in a false vacuum has in fact been known for about 50 years. But some recent developments have generated renewed interest in this subject. So let me describe that first. And these developments essentially began from the 2012 experiment at CERN, which discovered the first example of a scalar field in nature, that is a Higgs field. Okay. So once you have a scalar field, it has some potential, and we can ask, are we living in the false vacuum of this field? Now, it turns out that to determine the shape of the potential, you have to know the parameters of the theory well. Okay. And the current measurements, okay, have sufficient error that prevents us from coming to a definite conclusion. Okay. Nevertheless, if one takes the central value of the measured parameters of the Higgs potential, okay, then that shows that we are indeed living in the false vacuum of the Higgs field. Okay. Which means that the universe that we are living in is not in a stable phase, right? It is called what is called the metastable phase, and it is in principle possible that one day a bubble will form and will destroy the whole universe. But one can also calculate the probability of this happening, okay, and one finds, again based on the central value of the measurement, this can change in the future, okay, but based on the central values of the parameters that we get from the measurement, we find that the probability of forming a killer bubble is in fact extremely small. It's of the order of 1 in 10 to the 1000. And so it's highly unlikely that such killer bubbles will destroy us before the natural end of life in the last planet. Okay, because way before such killer bubble destroys us, I think we'll die anyway. Okay, so you shouldn't worry too much about such killer bubbles. However, the story is more complicated. It's more complicated because there are theoretical reasons to believe that there may be many more scalar fields in our theory. We have discovered only the Higgs field, okay, but there are theoretical reasons to believe that there are many more scalar fields that we haven't discovered yet. We have to go to higher energy to discover those scalar fields. Okay. And among these unknown fields, there may be some whose false vacuum describes us. So having more scalar fields means that the potential that I showed you, right, as a function of one variable, okay, should really be thought of as a function of many variables, because there are many directions in which you can go, and so this has many ups and downs, right? They are function of many variables, and each of those local minimum, right, will be like a false vacuum, right? Only the one with the lowest minimum will be the true vacuum, right? There will be no killer bubble that can destroy the one that is in the true minimum. So we don't know, okay, whether there are such false vacuum, okay, or whether we are looking in such false vacuum or where the true vacuum really is. Okay. And the probability of producing killer bubble for these fields may be large enough to cause us worries. So again, we go back to this question, are we living in a false vacuum? Okay. Now we could answer this question if we had a fundamental theory. Okay. So what we mean by a fundamental theory, okay, is a theory where the list of fields and the potential will be fixed from some fundamental principles. Okay. So that even though we haven't discovered those scalar fields, right, if there are some fundamental theory which told us what those scalar fields are, right, what their potential is, then we could calculate and see how much probability is there that will someday tunnel out and go to one of these other vacuum. Now, string theory is an attempt to have such a fundamental theory. It's a proposal for a theory that describes all the elementary particles and their forces, which includes gravitational force. In fact, this is one of the main successes of string theory, that it can combine gravity and quantum mechanics. And according to our current understanding of the theory, string theory has many scalar fields with complicated potential with many local maxima and minima. So this is sometimes called the landscape of vacua in string theory. So here I have only drawn one direction with many ups and downs, but the true picture is that there are many scalar fields in this theory with many minima. Okay. And what we have explored so far really is some local regions around given minima. Right? We don't know the full structure of this potential. Right? In theoretically, we can explore around a given minimum what the other minima are around a given minimum, okay, but not the global structure. Okay, that's the theoretical limitation of the theory at present. So if string theory is right, okay, then one of these minima will have the phase of the theory where you are living. Unfortunately, we do not yet know of a phase that describes exactly the elementary particles we see. Okay. So in this picture, you can summarize by saying that even if string theory is the right theory of nature, okay, we do not know our position in the landscape. Right? We have theoretically explored various parts of the landscape. We understand various local regions, but we have not found one that describes the region where we are. Right? So we don't know which vacuum we are living in. Nevertheless, we are not totally in the dark, because discovery of dark energy tells us that in that phase we are in the phase we are living in, the potential is positive. This I have already said. The dark energy density is positive, okay, and that is the value of the potential at the minimum. Okay, so we certainly know that if string theory is right, then the phase that we are living in, the potential energy density is positive. We also know from theoretical studies that string theory has many phases or many vacua, many local minimum, which have zero energy or negative energy density. Okay, where the potential takes zero value or negative value. Okay. So combining this experimental observation that our cosmological constant or dark energy is positive, okay, with the theoretical result in string theory that there are many minima where the potential energy density is negative, okay, already tells us that we must be living in a false vacuum. Okay, because you are not lowest. Okay, because we certainly know of existence of vacua which are lower than us. So if we accept that we are living in a false vacuum, okay, then the question that we will be interested in is how likely is it that we shall be hit by a killer bubble during the next 1 year, okay, or next 10 years, right? You can frame your question depending on your time scale. As I said, to answer this, we need to know our position in the landscape. Right? If we knew our position in the landscape, we could use string theory to calculate the transition probability to different nearby minima and calculate what this probability is. Okay? But we do not know our position in the landscape. Okay, so we cannot use string theory to directly answer this question. The best we can do at this stage, okay, is to use the experimental knowledge that comes from the age of the universe. Okay. We know that today the universe that we are living in is about 14 billion years old. So we can say that unless you have been extremely lucky, the risk of a hit per year must be less than 1 in 10 to the 10. Right? Because otherwise you would have been wiped out by now. Right? If the risk of being hit by a killer bubble had been larger than 1 in 10 to the 10, right, then most likely you would have been hit. So 1 in 10 to the 10 is a small number, right? But we can ask how small is this number, right? We don't really think of these large numbers or such small numbers in day-to-day life. So here is a way to understand how small this number is. So imagine that one day you hear that a small asteroid will hit the Earth and it will destroy everything within 100-meter radius of impact, right? But you don't know where it will hit. So the chance that you will be within that region is about 1 in 10 to the 10. So if you hear of an asteroid hitting the Earth, and if you worry that what will happen if it falls on you, right, then you should also worry what will happen if the killer bubble will appear within the next 1 year. It turns out that the actual story is a bit more scary, because as time progresses, the chance of being hit by a killer bubble in the next 1 year is in fact increasing. Right? Now this may sound surprising because the probability of decay usually doesn't depend on time. Right? A radioactive atom, for example, right, it has a half-life, but the half-life doesn't depend on how long it has lived. Okay? But in this problem, it turns out that the half-life or the decay probability does depend on how long the universe has lived, and that's because the universe is time dependent, right? It's evolving with time. Okay? So the more time passes, okay, the bubbles that are produced farther away can reach us, right? And that's the reason why essentially the probability of being hit by a killer bubble increases with time. Okay? So a simple calculation tells us that the risk today is about 3.7 times larger than the past average risk. Okay? So this past average risk is what you should think of as 1 in 10 to the 10, right? Because this fact that the probability is less than 1 in 10 to the 10, okay, is based on the fact that the universe has not been hit by a killer bubble in the past. Okay? So today the risk is about 3.7 times larger, and the risk in the far future will be about 15 times larger than the current value, right, which is about 60 times larger than the past average risk. So you see that life in this universe is getting more risky. Now I promised you that the quantum world will be more exciting and adventurous. So I hope you will agree that the possibility, however small it may be, that tomorrow will may be wiped out by a killer bubble, and the rest of the universe will share the same fate, is more exciting than waiting for a slow death over billions of years. So this is the exciting part. Okay, but I also promised you adventure. Right? So let's now turn to the last topic, which is the adventure. Now it turns out that as in most adventures, we need to leave home. So let's recall some of the facts that we learned earlier. The first fact we learned is that at present, we can access a certain region of the universe that is given by our horizon size. Okay, that's about 18 million light years. Right? In principle, we can send out signal up to 18 billion light years. We also learned that with time, the expansion of the universe will convert this into a multiverse with many universes, because at 18 billion light years, right, will become much larger in the future. Horizon will still remain 18 billion light years. Right? So in the future, we will have many multiverses inside today what we think of as one universe. We also saw that so the rate of increase of the number of distinct universes is essentially controlled by the expansion rate of the universe. Okay, so the universe will double in about every 12 billion years, right? So in every 12 billion years in the future, you will create 8 copies of our universe, right? So there will be 8 multiverses within our single universe every 12 billion years. Okay, so that is the multiplication rate of the number of universes that you can have. We also learned that there may be killer bubbles produced, and these will make some of these universes unlivable. Okay, once a killer bubble forms inside a given universe, right, it will expand at the speed of light, okay, and it will destroy everything within the 18 billion light years of where it was created. Okay, but it will not be able to go beyond. Right, so it is not going to destroy all the universes, okay, in a given system. Right, if there are 100 universes, it will destroy one of them. Okay. Now, of course, there may be another killer bubble independently produced somewhere else, right, which will destroy the other universe. Okay. But a single killer bubble can only destroy one universe at a time. The rate of destruction is not known at present. Okay, this requires understanding fundamental physics. Now, if the rate of universe production exceeds the rate of destruction, then the number of livable universes will increase with time. right? So you know this, the rate of universe production we know, this one you don't know, okay? But assuming that this is larger than the rate of destruction, we see that the number of livable universes will increase with time. Okay? So there will always be some livable universes that we can access. Now the question is, how does this help us? Okay, it turns out that it doesn't help us if we are lazy. If we remain confined within our galaxy, okay, then our annihilation probability will essentially be controlled by the rate. Okay, the fact that we are creating all these other universes elsewhere, right, will be of no help, because the probability of producing a killer bubble within our universe is fixed, given by the fundamental physics, and that will determine what is our probability of getting destroyed. Now, of course, it may be small enough so that the killer bubble reaches us after life in our galaxy has ended anyway. Okay, in that case, we do not care. Okay. But it will be a pity if we perish when life is still thriving in some corner of the galaxy, and the killer bubble suddenly comes and kills us. So at present, the only known way to overcome this, okay, and I say only known way because we do not, the quantum probabilities, right, are probabilistic by nature. We have no idea where the killer bubble might fall. Okay. We have no way to control the formation of the killer bubble. We cannot reduce the probability. At least there is no known physical way by which you can reduce the probability of producing a killer bubble. So the only known way to overcome this is to spread out in the currently accessible universe, right, which I said is 18 million light years. Over time, this region will split into many universes. Okay. And there we saw that once it happens, that even if some of them are destroyed by the killer bubble, the others will survive. Okay. And this way we can extend the collective life expectancy of our civilization. Okay. And this is the best we can do at present. Okay. By spreading out, we can reduce the probability that all the civilizations will be destroyed at one time. In fact, there is a simple calculation, okay, which shows that if we manage to spread into n universes, then that increases the collective life expectancy by a factor of this. Okay, this is a factor that we gain, right? So even if by spreading into 2 universes, right, the collective life expectancy, okay, will go to 1.5 times the life expectancy that we have by living in a single universe. So this is the story of the future. So I'll end by saying that the real hero of the story is dark energy, right? Even if we manage to spread out, right, the reason that it helps by spreading out is that dark energy creates all these multiverses, right? Without dark energy, there will be no multiverse, there will be no horizon, and a single killer bubble will destroy the entire universe. Nevertheless, our role will not be totally insignificant, because as we saw, dark energy only helps those who help themselves. So in your spare time, think of ways to populate the universe within our horizon. Thank you.
Now it's time for some questions.
If someone, like some crazy scientist, wanted to make like a vacuum collapse, then what parameters must he try to control?
Yeah, so it is not completely understood because you have to understand the theory very well, right? But if you understand the theory very well, right, then it is possible that by making very, very high energy region in one, okay, so if you look at this picture, right, the A and B. Yeah, so you want to go from A to B, right? As I said, what I described is a quantum tunneling. Okay? But suppose you don't want to wait for quantum tunneling, right? You want to destroy the universe by yourself, right? What you can do in principle is to pump in enough energy, right, in some small region, where it can classically climb up the hill and go there. Yeah, that's in principle possible, right? In practice, it's very hard, right? But it is, I mean, if you want to destroy the world, that's the way to do it.
More questions?
It is not possible to
communicate between the
yes.
multiverses. But from a point center, the multiverse is a sphere of existence. Means X is an 18 billion.
Yes.
But from X, the person who is standing at X plus dx distance, for that person, the multiverse will be X plus dx.
Yes.
So if somebody communicates with the person, like A person is standing at this position and B person is standing here. So if this person is communicating with this person, so this person will be able to communicate because his multiverse is not then that sphere. He will be able, or he or she will be able to communicate with the person X plus dx distance away. So is it, but then actually A information of A is sent to X plus dx distance.
Yeah. Okay. So the answer to this is the multiverse is not a static system, right? A given, so at each time, at a given time, you can access certain region. At a later time, you will be able to access a lower region because that region has expanded away, right? So if A communicates with B, right, that takes time. So by the time B receives the signal, right, the multiverse size of B, effective multiverse size has shrunk, right? So it will not, so B will not be able to communicate what used to be B's multiverse at the time when A sent the signal, because the signal from A will take some time to reach B, right? By that time, that region will become expand away, right? And the actual multiverse of B will be smaller in size.
Can we compensate the rate of expansion by somehow, so that it is possible? Rate of expansion, if we keep the distance smaller, then can we compensate?
Even then, see this 10 to the 18 billion light years, sorry, the 18 billion light years, right? That's a fixed limit, right? At any given time, you can access 18 billion light years. A little later, you will be able to access 18 billion light years, but that's smaller in size compared to what it was earlier, right? Because what was 18 billion light years has expanded away, right? So if A can communicate with B and B can send the signal, that's as good as saying that A sends the signal, right? Because the signal propagates at the speed of light, right? So whatever you do, right, the fact that A cannot send signal faster than the speed of light to certain regions cannot be overcome by having an intermediary B, right? Because that time from A to B also has to be taken into account.
Any more questions? Yeah.
Does string theory admit positive cosmology constant solutions?
Pardon? Does string theory admit? Yeah. So there are solutions in string theory which has been proposed which admit positive cosmological constant. Okay? But the major problem with those is that those don't have any fixed parameters, so they don't have parametric control. Right? That which basically means that you cannot have a small parameter that you can adjust, and that's because string theory doesn't really have a coupling constant. Right? Everything is determined in string theory from first principle, and this is not unlike our nature, because our nature also doesn't have a parameter. Right? All the parameters that we know of nature are all fixed numbers. Right? The reason that we can explore nature, right, with the quantum field theory and perturbation theory is that it so happens that some of the parameters are small. Okay? The fine structure constant is small, the weak interaction coupling constant is small, so you can expand in those parameters. Okay? But we cannot make, they are not arbitrarily small, right? So you know that they are all asymptotic expansions, and at some point those expansions will break down. Okay? So string theory is similar, that we have solutions to positive cosmological constant, but we cannot have parametric control. We don't have a completely systematic perturbation expansion that we can perform around those particular vacuum.
So you said that we don't know the full structure of the potential, but do we know the total number of independent scalar potential which are in play here?
No, because we only explore the scalars that are there, the structure of the potential around each minimum. Right? We identify, so the way string theory explores this is you find a minimum, right, which is a particular solution, and then we can explore the structure of the potential around that minimum. Right? You know what are the nearby minimum to that, but the global structure is still not known.
I'm asking about whether do we know how many independent potential are present? Do we know for sure how many? Like sometimes I heard that string theory requires some like 11 dimension of space and time, something like that. So are we?
Yeah. So 11 dimension is the physical dimension of space and time. Right. So string theory has many solutions. One of the solutions, one of these minima of the potential corresponds to 11 dimensional space time. I can put it that way. Right. As I said, this has many phases. So one of the minima corresponds to 11 dimensional space time, but other minima correspond to 4 dimensional space time. Right? There are some other minima which may correspond to 6 dimensional space time. So each of these have some properties, right, which can be widely different, right, including the dimension of space time.
So in the beginning, you said that when the universe is expanding, but the dark energy density is still constant.
Yes.
But the universe is expanding. So that means dark energy itself is increasing somehow.
Total dark energy is increasing.
Yeah.
Yes.
How is it increasing? Like the normal energy that's conserved, but dark energy is increasing.
Yeah. So the way it is increasing, the reason that it happens is because of this negative pressure, right? So if you have an expanding gas, for example, right, you know that its energy reduces, right, because the pressure is doing some work against the expansion, right? Now, if the pressure was negative, right, then it is doing negative work as it's expanding, right? And that means that energy can increase, right, if it's doing negative work. And it turns out that the relation between pressure and energy density is such for this dark energy is that negative, the gain in the energy exactly compensates for the loss that you will have because of the expansion, right? So if the distance go from A to B, right, if you just took into account the expansion, it will because the energy density will become A cube over B cube, right? Because there is 3-dimensional volume, but that is exactly compensated by the amount of work, negative work that the pressure is doing. Okay, and that's the reason, that's the way the dark energy density remains constant.
So when we try to measure the expansion rate of the universe, we find that the measurements from the local universe do not match with the early universe. So does string theory have any answer to that question?
No, I think that is not really the domain of string theory as such. Right now, we have to understand the experimental facts, whether they are really true or not. Right? I think that people are still debating whether that observation is true or not. If that observation is true, then that means our current understanding that the universe is made of only these 3 components, the dark matter and ordinary matter and dark energy, that has to be changed, right? Maybe there is some other form of matter has to be included. Right? So that is still not completely clear, right? Whether there is even a conflict or not, I think even the experimentalists don't agree among themselves, right? So once the experimentalists agree, right, then the theorists have to figure out what else is there that contributes to the expansion of the universe, right? Besides these 3 components that I mentioned.
So inside the isolated multiverses, would quantum entanglement hold?
Yes, that we still don't understand fully, right? So I think if I understand your question correctly, you will probably ask that if you have one system here and another system in, okay, you can start with an entangled system in a single universe, and then as the universe expands, they can become part of different universes, right? And they do still remain entangled, right? It is believed that they remain entangled, right? But exactly the physics of that is not understood, right? That's a question of combining gravity and quantum mechanics successfully, right? And I think this part, I mean, how the entanglement changes as the universe expands, that is still not fully understood. And I should also add that there is also this feature that whenever there is dark energy, right, where this universe is expanding like this, there is a background temperature that you cannot get rid of, right? Even if you have a completely cold universe, because of the expansion because of the presence of the dark energy, there's a background temperature, which means there's a background radiation, and that tends to decohere the entanglement, right? So again, that shows that the usual idea that you can entangle a system and that remains forever is not true in the presence of dark energy.
Sir, you told that the string theory supports the idea of ever-expanding multiverse. So, does it also support the idea of like cyclic universe? And if it does, like, what does it favor more, the string theory part?
No, I don't know of any way to incorporate cyclic universe within string theory.
Okay. And also, if we look at the killer bubble consuming the any universe, like out of the many multiverses, can we predict like that of our universe will be consumed sooner as compared to other universes?
Okay, typically if you think of the different universes having different minimum, see, as long as if you have a given minimum, right, then the probabilities determine once and for all, right? That doesn't depend on whether you are in this part of the universe or another part of the universe. Okay? But it may happen that these different regions of the universe, different multiverses, that one may have a higher potential than the other one. Right? Imagine that we start from our universe, right? And then at some point, some part of the multiverse, one of the multiverses, one of the universe in the multiverse makes a phase transition go to a lower minimum. Okay? Then that can also go to another minimum later, right? Because a killer bubble may convert the system from A to B, but there may be system C, the minimum C sitting somewhere lower, right? It can make transition from B to C. So that you can compare whether the probability of a killer bubble forming in A is larger or smaller than the probability of killer bubble forming in B. That you can calculate from microscopic calculation. And that depends on whether, when you say whether it's our universe or another universe, that depends on which universe you are comparing with. It's not always the height, because it's also the barrier. Height and the width. Exactly. Well, by A and B, I meant the whole system, the complete information about A and B, right? That around the minimum A, right, there may be different directions, right? And you look at all the possible minima around in that environment. And similarly, for the other B, you look at its environments, right? All the possible minima, and then you have to calculate the fastest probability, transition probability, and then compare the two. But in different directions. It's not two variables, because it's a multidimensional potential, right? So it's not one height and one width, right? You have to find the minimum tunneling distance.
Hello, sir. Yeah. Sir, as you given that model of bubble, so what that factor is which is expanding that bubble?
What that
factor is which is expanding that bubble?
Oh, that is just classical dynamics, because as I said, oh, maybe this has somehow gone away. Yeah. So once this bubble is formed, okay, then the bubble will always try to minimize its potential energy, right? And because the potential energy density is lower inside, okay, than outside, having it expand lowers the potential energy, right? So that is a driving factor. Okay. This competes with the surface energy, because as the bubble wall expands, the surface energy goes up. Okay. But once the volume is sufficiently large, then you always gain more negative potential energy by expanding, and that is a factor which drives it. Yes, okay, just because any system tries to go towards lower potential.
Sir, is there any evidence that killer bubble has destroyed our universe?
No, because if it did, we'll be hit by the killer bubble, right? Because you see, the killer bubble wall expands at the speed of light, right? And any signal also expands at the speed of light, okay, right? So there can be no direct evidence that a killer bubble has destroyed the world, because then that will also destroy us, right? Because the signal will propagate at the same speed as the killer bubble itself. But there are, of course, theoretical predictions that even we may be killer bubble inside some other universe, right? That's certainly possible, that our universe was produced by producing a bubble in some big universe.
Sir, I wish to ask, what exactly does this potential energy and surface tension mean here?
No, this is not due to gravity. You can just think of ordinary scalar field, right, which has a potential energy density, just like if you have an electromagnetic field, right? Then the energy density, you know, is integral of E square plus B square, right? For electromagnetic field energy density, it's similar to that, right? The potential, the V, this function V of phi, it basically tells you that there's an inherent energy density in the scalar field, right? And that is what is contributing to both the energy density in B and energy density in A. Now, what about the surface tension? The surface tension is coming because the scalar fields also have a term, there is a contribution to potential energy density from the gradient, right? If the scalar field has a gradient, then that also contributes to energy. And if the field has to change from B to A, you see the field A is this value of the field, right? And B is this value of the field. So if it has to go from A to B, right, across the surface, then it has to have a gradient. That gradient is the surface tension. Right? This is what I meant by surface tension. No, it is affecting us also, because this potential energy density, for example, will also tell us that if we scatter particles, right, what kind of scattering it will have. So it is certainly affecting the microscopic physics also.
So when you said the distance, the origin is something like 1.8 into, you said some value, right?
Yes.
So where is the center of that expansion? Is it essentially, are you saying that Earth is at the center of that expansion, or that where is the distance?
No, there is no center. See, there is no center. It's like expanding surface of a balloon, right? It expands in all directions. You think of, we are living in a surface of a balloon. So any point is as good as any other point. Okay? And from any point, you can go up to 18 million light years. Right? So we don't play any special role in that calculation. Okay? From any point of the universe, you can go only up to 10 to 18 billion light years. So there is really no center.
So I know there will be many more questions, but we have to extremely thankful to Professor Sen,
Thank you.
Just explaining this very complicated concept without having a single equation. Thank you, sir. Thank you very much. Now I invite our director, Professor Deepankar Banerjee, to felicitate our speaker.
Thank you very much.
Yeah, thank you, sir. And thank you all for this wonderful gathering, and thank you, sir, again for this wonderful lecture. Thank you very much. Sir, do you have time with the intro?
Depends on Naveen and all.
Naveen, okay.
When he says that I have to go.